Okay, so what we have here is we have a beam with both a flat distributed load and a triangular distributed load, and a point moment and a point load there at the end. And what we need to do is we need to draw our shear and moment diagrams for that. That's what we're going over in this video. I also have the steps for drawing shear and moment diagrams down in the description. You can check that out. I'm sure you'll find that helpful. So if you do, hit that like button and don't forget to subscribe. Helps me out a lot. So the first thing we need to do is we need to draw our free body diagram, like in all drawing our shear and moment diagrams. That's the first step we need to do. So we will draw it up here so that we can draw our shear and moment diagrams underneath it. So we have our distributed load on the first third of it, and then our triangular distributed load, and then we'll make this just a little bit longer to look proportional. And we have our point load, which is 600 pounds, and our point moment, which is 450 pound-feet. And then our distributed load, our flat one, is 350 pounds per foot, or 300 pounds per foot. And then we have our reaction forces here 1/3 along the way. We'll call this A sub y. And then we have our one at B, we'll call it B sub y. Now we need to solve for the reaction forces, and we'll do that using equilibrium equations. So first we'll solve or sum forces or moments about point A so that we can solve for the reaction force B. Set that equal to 0 because it is in equilibrium. And then we have our distributed load here from 0 to A, or from this end to A, and it is 300 pounds per feet, and it is 3 feet long, so that's 900 pounds. It is going to cause counterclockwise rotation about point A. We'll say that's a positive moment, so we will say positive 900 multiplied. Its center of gravity is 1.5 feet away from A, so I'll multiply by 1.5. Then we have B sub y, which is also going to cause a counterclockwise rotation, which we said was positive, so plus B sub y times by its distance, which is 3 feet. Then we have our triangular distributed load. It will start at 300 feet, or 300 pounds at this end, and it is 3 feet long, so solving for that triangle is the area of that triangle is half the base times the height. So 1.5 times by 300 is 450. So that is going to cause counterclockwise rotation, or clockwise rotation, so we'll say it's negative. So negative 450. Its center of gravity is 1/3 along its length away from the right triangle part, right angle of that triangle. So 1/3 along its length is 1. Then we have our point load right there, which is 600, and is going to cause clockwise rotation, which is negative. So 600 times by its distance away, which is 6 feet. And then finally we have our point moment, which is going in a clockwise rotation as well, so it is negative. So minus 450. So add these all up and solve for B sub y. You get that B sub y equals 1,050 pounds. Now we can sum moments in, or sum forces in the y direction and solve for A sub y. So sum of the forces in the y direction equals 0 because it is in equilibrium. You have A sub y, which is in the positive y direction, and B sub y, which is also in the positive y direction. And then minus, we found that this is pushing down with 900 pounds of force, so minus 900. This is 450, minus 450, and then minus the 600. And remember that the point moment it's not going to affect our forces in the y direction. So solve for A sub y, and you get that that equals 900 pounds. So we'll label that right here on our free body diagram, and below it we will draw our shear moment diagrams and their axes and label them. So we have our axes, and now we are going to start with our shear diagram on the left hand side. So on our beam we have our distributed load on that side, and the beam doesn't have any supports on this end, so it's not going to resist any shear. So it's going to start at 0. The internal forces at the end of the beam are going to be 0. And then it's going to start going down because of this distributed load. Remember that this is, because it's pushing down, our shear diagram is going to go down, and the amount it's going to go down is the area under our loading curve, which we found was 900. So it's going to drop 900 pounds. So we're going to label that here as negative 900 over 3 feet. And then because this has a slope of 0, this is going to have a constant linear slope, and it's just going to go straight over to that point, down 900 and over 3 feet. This A sub y reaction force is going to push it up 900 feet, so it's going to bring it back to 0. And then we have our triangular distributed load, which is also a negative area, and we're going to draw that right over here because from an engineering standpoint it makes sense to draw this above the beam because it's probably weight on top of the beam. But from a calculus standpoint it doesn't make much sense because this is actually a negative area, so it is more helpful to draw like this for that, thinking about it that way. Because this is negative area, it's going to drop it down. The amount it's going to drop down is the area under this curve, which we found is 450. This is a positive slope, which is why this comes in handy, because this looks like it's a negative slope, but it's actually a positive slope, meaning that it's going to be concave up. So it's going to drop down to negative 450 because the area is 450 under there, and over 3 feet is something like this, and it's concave up, so it will look something like that. And then we have our B sub y reaction, which is going to push it up 1,050 pounds. 450 plus 1,050 is 600. So it's going to go up here to 600. We'll label that on that side. It's going to go up to here. And then from our B sub y reaction over to the end, nothing changes. Just going to draw a straight line. And then this 600 pound force is going to push it down 600. And that will bring us down to 0. And because this end is free floating, it's not supported by anything, we know that the internal forces are also going to be 0, just like it was at this end. So that's one way we know that we did it right. So moving on to our moment diagram, once again, it's not supported at this end, so it's not going to have internal moments there. Our moment diagram is going to start at 0. This is negative area, so it's going to push it down. This is a negative slope, so it's going to be concave down, and the area under this curve is 900 times by 3, because it's 900 on this side of the triangle, 3 on this side of the triangle, and so the area is half the base times the height. That is 2,700 divided by 2, which is 1,350. So label that here, 1,350. Going to this point, and we said it was concave down because it has a negative slope, so it'll look something like this. With this area, probably the best way to find the area under this curve is to draw or come up with an equation for our loading function for that triangular distributed load. And we already still have our picture here, so we will say that this is W for our loading function. It is function of x. And for simplicity, we'll say here at A is 0, and then going over is x to the right. So our slope it is going up, up 300 and over 3 feet. So rise over run, 300 divided by 3 equals 100. So that is going to be our slope, is 100x. It is positive 100x. And it starts down here at negative 300. Remember, because that's the height of our distributed load. So here we have our loading function. For our shear function, we're just going to integrate the loading function. So that will be 50x minus 300, or 50x squared minus 300x. Our boundary conditions for this, we know that this starts at 0 on our shear function, so our plus c, which is our boundary condition, is just going to equal 0. So this is our shear function. Now to get our moment function, we, to know where this ends up, we know the shape of it because this is negative area, so it's going to push it down. This has got a negative slope, so it's going to be concave down once again, which is opposite of this. This is concave up. But we need to know how much farther it drops down. So we can do that one of two ways. We can integrate our shear function and find the area under the curve here, and then subtract it from here. So we integrate it from 1 to 3. Or we can just find the moment function and plug in at 3 for x to find what the value is at x equals, or what our moment is at x equals 3. So integrating, we'll need to do that either way. Get that 50 divided by 3, x cubed minus 150x squared. And then our boundary conditions, this starts at negative 1,350, so minus 1,350. We're just going to plug in 3 for x, and then you get that our moment function at 3 equals 2,250 pound-feet. So we'll label that here on our axis, negative 2,250. That's going to end up right around here. We said it was concave down, so it's going to go like that. Then finally we have just the area under this part of the curve. It is flat, so 600 times by its length, which is 3, that's 1,800. 2,250 plus 1,800 is negative 450. So it's going to go all the way up here. Remember, this is flat, so this is going to have a linear slope. So this is going to be negative 450. We will just label that here. And you can probably guess by now, because we already said that the ends can't support moments, it is going to jump up because of this 450 point moment. But the reason why it jumps up is because in the beginning we said that a positive moment was counterclockwise. Well, this moment is going clockwise, so we'll say that this is a negative moment. Well, this is an external force, but we are drawing our internal forces. That's what, well, our internal shear forces and our internal bending moments. And so our internal moments have to resist the external moments. So the internal forces in the beam are going to be pushing in the opposite direction of this one. This one's pushing clockwise, and so our internal for bending moments is pushing counterclockwise, which we said is positive. And so because our internal bending moments are positive, it is going to be a positive jump in our shear or our moment diagram. Just like that, and that completes our moment diagram. So I hope you found this helpful. If you did, hit that like button. I've got the steps written down in the description for how to draw shear moment diagrams. I'm sure that you'll find that helpful, along with all the calculus tips and tricks that help us draw these diagrams way more easily. So if you have any questions or suggestions, leave them down in the comments. I've also been creating some awesome designs with student engineering logo, like the one on the shirt. If you're interested in buying stuff like this on shirts and hoodies and mugs and stickers and other stuff, you can buy them through the links in the description from Amazon and Teespring, and that helps me out a lot. I've also been creating some project videos that you can check out on my channel, building 3D printed boats and stuff, and that's pretty cool. You should check that out. If you're new to this channel, my name is Preston Palmer, student engineering, and my goal is to help other engineering students like me better understand engineering. So if you found this video helpful, hit that like button and please subscribe.